4 of the tutorial on implementing a functional language in Scala. In this part, we implement evaluation of expressions. So just a comment here is that in µDhall as well as in Dhall, evaluation is guaranteed to work correctly or to work at all only when the expression has been type checked and found to be well typed. If the expression does not have correct types, then it is not guaranteed that you can evaluate that expression at all. So an example would be if you say 10 plus x, but x does not have the type of natural, then it is invalid to add 10 plus x, and it cannot be evaluated. So the type checking stage is necessary to ensure that all expressions are well typed and can be evaluated. However, the evaluation itself does not use types from the type checking. So we do not need to know the types of anything when we evaluate µDhall. This is a very much special situation. That is not always like that when you evaluate, you don't need to know any types. But in this case, it is like that. Also in Dhall, currently, it is like that. So evaluation can be implemented without implementing the type checking. And just assuming that type checking has been performed and the expressions that we are evaluating have correct types. And so that's why we do evaluation without having implemented type checking. On the other hand, as we will see in the next part, type checking requires already to have evaluation, because in some cases type expressions need to be evaluated before you check that they are correct. So let us proceed and go to evaluation. So evaluation has 3 rules in µDhall. First of all, function applications are evaluated by substituting the variables, and we already have implemented the substitution function for this. Secondly, built-in operations and functions are evaluated, and each of them has a specific meaning. So for example, 10 plus 20, it is an addition of integers that should give you 30, and natural subtract, it is subtracting 1 from 2, and that is, again, it has a specific meaning. So all these built-in functions need to be evaluated according to how they are defined specifically. And finally, we have a final rule that if the result, after applying all these rules, if the result still contains any lambdas, any bound variables and functions, then we need to perform what's called alpha-normalization, which is we rename all bound variables to underscore, and we introduce correct De Bruijn indices so that we don't have any name clashes and all the variables are still bound correctly. And that is always possible. The result of this will be an expression that doesn't have any variable names. All variables are just underscore with some index. And it doesn't have any let expressions, because all the let expressions have been substituted. It doesn't have any functions applied to any argument, because all functions have been applied. But it might have some lambdas still. And so inside lambdas, there could be still operations and function applications and more lambdas, but not let expressions, because we substitute them. So that is what's called a normal form. It's a normal form that cannot be evaluated or simplified any further. In most cases, it will be some simple expression, like a number, or maybe a simple lambda. But in some cases, the normal form is actually being very long. And this is because evaluation is symbolic. And here's an example of what it means that evaluation is symbolic. So suppose we have this expression. So this expression is a lambda, which takes x, then it makes another lambda and applies that to 123. So 123 is substituted instead of y. So then you have x plus 123. And finally, you replace x with an underscore, and you get this function. So this is the normal form of that expression. It is simplified as much as possible. And here's an example where we would introduce non-zero de Bruijn indices. Here's a lambda a, lambda b, a. So we rename, there's nothing to substitute, so we just rename variables. A becomes underscore, b becomes underscore, and this a becomes underscore at 1. So this is a case when we need to increment the de Bruijn index. And this, for example, is another case where we have to increment. So the technical terms are beta-normalization, which is substituting, and alpha-normalization, which is renaming bound variables. And so we're going to adapt the Dhall rules and specification. For example, here is a full specification of beta-normalization with even some Haskell code as examples. Substitution we have already seen. I'm going to reproduce the rules that apply to µDhall. I'm not going to look at the Dhall documentation because it's too much for us to look at. We just need the parts for µDhall, and I already prepared them. So how do we write the specification of what it means to substitute? So we write that as proof steps that descend into sub-expressions and show what happens when you evaluate expressions of different kinds in terms of sub-expressions. So this is known as small step semantics. So each of these are a small step of evaluation. You need many of those steps. So here's an example how we are going to write the rule. So again, the rule is a fraction where the denominator is what we want to prove, and the numerator shows things that we need to prove in order to get what we want. And so we introduce this notation, arrow with alpha and arrow with beta, which means one step of evaluation or reduction. So then, for example, we say a plus b. So how do we evaluate a plus b? So if a evaluates to 0 and b evaluates to b prime, then a plus b evaluates to b prime. So this is translated into code as a specific case in a pattern match with a recursive call of the same function. So a beta-normalization function takes a plus b, and then it applies beta-normalization to a and checks if that's 0. And if it's not 0, then we have a next rule, which is that a is beta normalized to some a prime. And then we also apply to beta, to b, and b is here normalized to some b prime and here to 0. But if none of them are normalized to 0, then we cannot use these rules, so we go to the next rules. And the next rules say a is normalized to a natural number, b is normalized to a natural number, and then we know what to do. We just add them according to the built-in operation of integer addition. And finally, there is a case where we applied by recursion the beta normalization to a, we get a prime, applied it to b, we got b prime, but a prime and b prime are neither 0 nor both natural numbers. And so we cannot simplify anymore, but we did simplify the parts, perhaps. So then we say, well, the result is a prime plus b prime, again, as a binary operation in the syntax tree. So this is how any expression of the type a plus b, so binary operation with a plus, any expression is reduced to its beta normal form. So it is important that we need to translate these rules as functions. So functions from input to output. And it is not always true that the rules can be translated in that way. We need to check if that is true, because this rule notation is not a function notation. It's not a code that says how to compute the function. It is just a notation that says these are, if a plus b is reduced to a prime, then you can prove that if you prove that if a is reduced to a prime and b is reduced to 0. If a, b, a prime are such that this is true, then you can reduce. But you don't know necessarily how to reduce. So this rule can be translated into code, because you see, if you apply this function to a, you get a prime. You apply this function to b, you get something, and you check if it's 0. If it is 0, then you apply this rule and you have the result. And if not, then there are some other rules. And looking at these 4 rules, we find that we have covered all possible cases. And so we actually have a way of translating this into code. And here's an example where a rule cannot be translated into code. Imagine we had a rule like this. We don't, actually, but if we had, then it would not be algorithmic. So usually one doesn't write rules like this, but in some systems there are rules like this. So, for example, if I say A is reduced to C, if I can prove that A is reduced to B and that C is reduced to B. But I don't know what C is, and I cannot use this rule. So if I'm given A, I need to find what C is. So I can reduce A to B, but then I'm supposed to guess what C must be such that it is also reduced to B. But I cannot guess that. There are infinitely many possible expressions to check. And so I cannot translate this rule to an algorithm. The C in this rule is on the left-hand side, and that is not good. So it needs to be on the right-hand side, and then I can translate that into an algorithm. So of course, in our case, all those rules that we have are going to be good. They're going to be translatable into functions. But in any case, this notation doesn't guarantee that rules are translated into functions. So it is implicit in this notation, and it needs to be checked. So what are the rules for alpha normalization? Well, free variables are actually not changed. Only the bound ones are changed. Then how do you alpha normalize a lambda? Now, you need to rename x into underscore. So maybe underscore already was present in B0, so then we have to shift the underscore in B0. Now, underscore is a variable name in µDhall. Excuse me. Perhaps I should explain. Underscore in some programming languages is used as a special symbol to say that some value is not used, or some value is missing, or something else. But not so in Dhall and not so in µDhall. Underscore is just a normal variable, and it can be used just as normal. So we need to rename that. We need to shift all occurrences of underscore in B1, because we're going to have a lambda in front of B1 with underscore bound. So we need to shift everything that was there. Then we substitute x, And then we have to shift x back because we have substituted it, but b0 could have had x in it. And now that x that we substituted, let's say, but b0 could have had x at 1, x at 2, and so on. And those need to be shifted down because now we are deleting one binder with x and we're adding one binder with underscore. So we need to shift up underscore and down x. And so that gives us some b3. And finally, this b3 needs to be alpha normalized as well because it could have some bound variables inside, some more lambdas. So this is the algorithm. It's really written like a function, more or less, but in this notation, in the formal proof notation. So we can translate that into any programming language pretty easily. But it will be much easier to translate into Scala than in many other languages because of pattern matching. So here is the translation. So you see this block is the same for all the three cases. So we just put that block into a helper function and then the code becomes very quick. And all the other cases, we just use map and apply the same function recursively to all the sub-expressions. So let's test this. If we have A, B, A, then the result is this. And if we have X to underscore, then the underscore must be shifted. And that is correct. So tests passed. So now we go to beta-normalization. The beta-normalization means we are substituting variables when we do let x equals a and b, so we substitute there. And we also substitute when we have a lambda that is applied to an argument explicitly. And we also change things and substitute when we have built-in functions. So let us write down exactly what's happening. So if we have a built-in carried function, it needs to be applied to all arguments. So if it's only applied to some arguments, it's not going to be evaluated. And also, built-in functions are evaluated only when at least some of those arguments are literal constants. So let me explain how we evaluate natural fold. Natural subtract I already showed. It's just subtracting natural numbers. Natural fold is a function that says we have a function g that needs to be applied to an argument b, and then the g needs to be applied n times. Now the capital B is a type of b, and g must have type b to b. So that is going to be checked on the type checking stage, so we can assume this is true. And so the natural fold is a loop in a sense. It applies a given function to a given value, and then it applies that function n times. And now, if n is a natural literal number, then we can evaluate this in this form. Otherwise, we will not evaluate at all. We will just evaluate sub-expressions and keep natural fold symbolic. So you can see in this way we implement symbolic computations. If we can simplify, we do. And if we cannot simplify, we just leave expressions as they are. And that is the core essence of symbolic computation. So for user-defined lambda functions, we need to substitute arguments into function bodies, and then we're done. Now there are some specific simplification rules for plus and for times. Like for example, we would like to multiply by 0 and we get 0. Even if the other argument is unknown, it doesn't matter. It's enough that one of them is 0. So we have, if multiplying by 1, that gives you the other argument simplified, and so on. So all these subtract, for example, if you subtract now, let me make a comment here. In µDhall, natural numbers are non-negative. So when you subtract, say 10 from 1, then you would normally get a -9, but there aren't any negative numbers, so natural subtract returns 0 in that case. So that's a kind of special case. So the rules for natural subtract are if both arguments, so so we say a rule, right, for a function applied to an argument, fb. If f is evaluated to natural subtract a, and if a is evaluated to m, and if b is evaluated to n, m and n being natural numbers, literal numbers, then we subtract them. If m is less than n, we subtract, and if m is greater than n, then we say the result is 0. And we have also special cases when we subtract 0, or we subtract from 0, or we subtract from equal numbers. So we subtract xx, where x and x are equal. So after beta and alpha normalization. Then, so this is a special operation which is defined that we perform beta and alpha normalization, and then we check just syntactic equality of two terms, and if they're equal, then this holds. So then the subtraction is 0. Natural fold we define. This is a kind of formal inductive definition, not necessarily a good implementation, but if so, natural fold 0 is just applies the function 0 times to the argument, which means that the argument is unchanged. We just reduce the argument and return that. And if we have natural fold 1 plus n, where 1 plus n is a non-zero number, then we do a recursive call. So we apply g to the result of natural fold with n, and then we reduce that, and then we get some t1, and that's the result. Now this is the definition. I will show how I will implement natural fold later in a more efficient way. So then how do you reduce when you have a lambda? So you have a function application f(a0), where f reduces to a lambda. Then you have to shift the a0, you shift x in it, because you're going to substitute that into the body. So you have to shift x, then you substitute a1 instead of x, and then you get some b1, and then you shift back in that b1, and you get b2, and you reduce b2 to b3, and that's the result. So these rules show you essentially how to compute a normalization for any expression. If an expression is a function application, then one of these rules must apply. If none of these rules apply, then you just perform beta reduction on each sub-expression, and the function application remains unevaluated. And final rule is, if you have a type annotation, then you drop it. You just drop all type annotations by evaluation. All right, so let's now implement this in Scala. These are the formal definitions, which are, you could argue this is also a programming language, but very special one. So let's translate that into Scala. So we define the equivalence function, which means that we just do an alpha normalize and beta normalize, and that must be equal as case classes, so syntactic equality, or as they call it, judgmental equality. Then here's this function that does a shift, substitute, and shift, which is used several times here, so I put that into a function. And then finally we do the beta normalization. So if the expression is annotated, so for example, that's the last rule. If it's annotated, then we just drop the type, and we know it has been checked, so it's correct. So we drop the type and we apply beta normalization to this value, t0, and we get t1, and then we return that. So that corresponds to this code. We just beta normalize e, and we just ignore t. Then let gives you a shift sub shift, which is this combination. Then there is a case where we have a function applied to argument, and in that case we have several subcases. So first we beta normalize the function, we beta normalize the argument, and then you see what happens. So if you beta normalize an argument and you get a lambda, it means you can substitute, and so you do the shift sub shift. And if that's a built-in function, then you do the rules for beta normalizing natural subtract, natural fold. So there's another one. So you have those rules. If no other rules can be used, then you already beta normalized f and b, and the result remains. So you just have an applied f and b, and it's the same as it was before, except for you. So it remains a symbolic application of a function to an argument, but the function possibly has been simplified and the argument possibly has been simplified. So the binary operation, we have those rules. What happens? So you beta normalize the two arguments, L and R, and then you match them with all the different special cases that we can simplify. So that's it. That's the entire code of beta normalization. And finally, you can test that this works by giving just text in µDhall. Since we already have parsing, we already have beta normalization and pretty printing, so we can just say, take this, parse it, beta normalize, pretty print, and you must get this. So now I give you a lot of tests, and all of these tests pass. So now you see, this is already quite far. We get natural fold. So for example, the last test is a symbolic fold, which means that we have a function that adds a to x, but a is free. A is never defined in this expression. So we say take 100 and apply 5 times the function that adds a. And so the result is 100 plus a plus a plus a plus a plus a plus a. So that is a symbolic expression that adds 5 times the unknown value a. And that is what beta normalization does. It's a symbolic evaluator. So when you can simplify, you simplify, and when you cannot simplify, then you just leave it symbolic. So here is another example of symbolic evaluation. 1 times x is evaluated to x, and x is unknown. And a function that takes x and returns x plus a, apply to 100, and it gets you 100 plus a. So this works as expected. So this concludes part 4, and the next part we will go and look at type checking.